Good morning, all. I hope everybody is doing well. This is Professor Bachman coming at you, and we're going to go over the first lecture today of the energy course. I'm usually going to do probably two lectures per week, except for this week and maybe the last week there because we're doing our presentations and stuff. Um, but because the way I'm going to structure this is, remember that we're going to, the first week we are going to, talk about the introduction, and then we're going to do coal, and then I'll do a separate one for natural gas, and a separate one for oil, and then finish natural gas, and a separate one for solar, a separate one for wind. So each segment of kind of energy we're going to do, I'll do a separate presentation. But this week we're just going to have one. Also, remember that underneath your PowerPoint presentations here on Blackboard, you'll be able to download the lecture PowerPoints. All right, but your videos will be in the class videos. Okay, so why don't we, let me see if I have this up already, get to it and start with lecture one here. Okay, on energy conversion and transportation. Okay. Oh, remember, we are not going to. I had a couple of people email me about this. We're not going to have like a video discussion or you have to log in at a certain time and talk with the class, unless you guys want to. If you guys feel that will be helpful for you, let me know. I'll have to figure out a way for me to be able to do that. Maybe I'll sign up for Zoom or something. Um, but I don't know if it's necessary or not, unless you guys want to. Remember, was I still want to do that like kind of class picnic thing, coming to my farm to see my solar panels and wind turbine and battery array and all that other stuff. And if you're interested in doing that, please let me know. I think that'd be fun to do. Okay, so let's get into lecture one. The tenets of sustainability and energy. So in this lecture, what I want to discuss, and hopefully you'll understand by the end of this, is some of the foundations and tenets of what's called sustainable development. That is the rubric I use in my everyday life. You don't have to use that rubric, but I want to make sure you guys know where I'm coming from, and it makes sense. Okay, it's all part of a well balanced critical thinking schedule when we're talking about energy, and I think you'll realize that. Okay. We'll talk about the importance of natural resources and the ecosystem services out there that help us out develop this, because we don't really, as human beings, we don't create anything. Okay, we just kind of move around the molecules and put them in a certain order so that we can utilize them. All right, but we don't create, we don't produce energy. Okay, it's always there. We just convert it from one state to another, and that is basically what I call our ecological niche as a species. Okay, we're able to use other forms of energy, and you'll hear about that in the one of the podcasts. I'll talk about that coming up. We'll talk about what is energy and where does it come from. We'll talk about the same scientific foundations and principles of matter and energy, and we'll talk about the different forms of energy and how it comes. Then we'll talk about, final wrap up about how the United States and the world. We'll talk about the United States and world energy consumption levels and how it's distributed around the world. Okay, so let's get at it. This is one of my favorite quotes from David Orr. It says, "When we heal this earth, we'll heal ourselves." And there's a lot of, I'm a ecological economist by trade, and I know I'm really worried about the environment. And this quote really makes a lot of sense to me. If we start trying to fix those things that are problems with climate change and our energy consumption and all this other stuff, boy, when we try to fix those things and get into the equilibrium of the way the world's supposed to be, we will start being nicer to each other. Okay, I think we'll find out we'll have a lot less wars, we'll be fighting over water, all this different stuff. Now, a lot of these problems that we have, this discrimination and things like that, I think some of that stuff will just magically melt away because we are starting to live within symbiosis of the earth. Okay, and that is basically the whole tenet of this word sustainable development I've been talking about. Okay, the basic definition of sustainable development is meeting the needs of the present without compromising the needs of the future. Okay, and the key to this word is the needs. So there's a lot of needs needs that individuals have. We need to have food, water, and clean air, right? Those are three needs. And I think, when we talk about when we make a society that's kind of like a given, everybody wants to have clean air, clean water, and good paying job, things like that. All right, there's all these little tiny needs that we need, and energy is definitely one of them. All right, but we've got to make sure in this energy mix that we use in the world today that we're not compromising our next generation from being able to produce that electricity efficiently and having clean air, water, and or a stable climate. Okay, so energy is definitely a need. It makes the world go round. Okay, and I'm not saying that everybody needs to have 5,000 calories to eat because they're all going to be weightlifters. When I do this rubric, I'm talking about the basic needs that we need as individuals to survive. Okay, the consumption level of the individual is basically up to them, but there is definitely a limit and a cutoff. We only have so many resources on this earth, and we have so many people, and if we want them all to be able to live a life of sustainability, of being able to live, we've got to make sure that they have a certain amount. Okay, so that's the amount I'm talking about when it comes to sustainability, sustainable development. Okay, and I'll be using this word sustainable development a lot. You also have a reading about that. You're going to get a crash course on the science of that, and also one on resilience is another one of your readings. And what I mean by that resilience is, I have a saying that biodiversity equals resilience, which equals sustainability. Meaning that the more diverse a mix is, the more resilient it will be to be able to bounce back from a disaster. And that's what gives us the sustainability. And this comes from an ecological principles of just the more biodiverse an area is, if there's a natural disaster, it's going to be able to bounce back better. Right? For example, if there's a hurricane that takes down the tropical force edge or something like that, there's a lot of that biodiversity in the tropical rainforest. So if there's a natural disaster that happens there, it's going to be able to bounce back and become the rainforest we once knew a lot faster. If something happens in the desert now, because there's less biodiversity, that's going to be harder because there's not as many species within inside that ecosystem for it to one of them to make it through that natural disaster. And we need to start thinking of our energy section just like that. We, as you'll find out, we rely on basically three fossil fuels. We need to diversify that energy if we are going to be able to sustain our energy consumptions that we like as humans right now. Okay? So we rely on natural resources as humans. Okay? Natural resources are the substance and energy sources that we take from the environment and rely on to survive. Right? So we don't produce any of these natural resources per se. Okay? We just extract them from the environment where Mother Nature has provided us, and then we use them to help our everyday lives. I mean, these can be either food, minerals, fossil fuels, or renewable energies such as trees, and yes, even human labor. And I have human labor here in the red because a lot of times when you look back in the history of economies and stuff like that, when we started thinking about this, it wasn't the Adam Smith's Wealth of Nations, it's called. It's one of the first economic books. The Wealth of the Nations didn't include labor per se. The wealth of the nation was how much food it could produce and minerals, and they didn't know about fossil fuels back then, but wood and trees and things like that. So putting human labor as a natural resource is kind of a newer thinking, but it definitely is in that thinking today. We have basically two different kinds of energies, okay? Broken into two different categories, I should say. There's what's called renewable natural resources, which are replenished over a short time, and typically inside a human life. So 100 years, a tree is considered renewable energy because every 100 years we can harvest it and take that out and make some more 2x4s so we can make some more houses. Okay. Sunlight is also considered a renewable energy, but that doesn't take 100 years. It just takes 12 hours to start shining its way onto this earth again, or wherever you're standing on this earth. So They are also considered inexhaustible, but in actuality, they are exhaustible. Okay, it's just that the sun isn't going to run out of energy for another billion years. So, in our thinking, we say they're inexhaustible, but remember, there is no thing. We'll learn this in the laws of physics. Tells us that every time we use energy, we need a little bit more. So the sun, slowly but surely, is using all of its energy, and sooner or later, in about a billion years, it will be have no energy. Okay, it will all be released back out into the atmosphere, out into the universe, and those molecules will manifest itself somewhere in another universe, and we'll have another Earth somewhere. Okay, so even renewable energies are exhaustible, but if we manage them properly, such as our timber and our water and animal populations, we can keep them sustainable. All right, we can keep them going until that sun finally washes out. And that's one of the things I studied in my doctorate was how do we do those sustainable models? How do we plant a forest so that we can have that every year? We can have some cutting happening. And what is that limitation on this many acres? All right. So we need to be careful because the story of the Lorax is definitely real. All right. We also have what's called non-renewable energies or natural resources, which are formed much lower, and they then we use them and are no longer available once depleted. They're kind of gone. All right. And even the four main ones are crude oil, natural gas, coal, and minerals. Okay. And we need to remember that these two are actually renewable. They just take a million years to form. All right, the coal, the natural gas, and the oil were just old biomass from a long time ago, and they got into the earth, and the earth moved them around, it's crushed them, and moved them, ooh, put them in a nice little pool down there. We're gonna suck it out with a straw. All right. So to say that non-renewable is kind of disingenuous. It just takes millions of years for them to actually form. All right. And once these are gone, they're considered gone. So the second law of thermodynamics says we can't create, everything goes into entropy. Just remember when we pull that coal out of the ground, we burn it to turn some turbines to make some electricity. We can't get that chunk of coal back, and not for another millions of years. Okay. Uh, in addition to the goods provided as resources from the natural systems out there, the environment also provides ecosystem services such as air, the water purification, cycling, nutrients, climate regulation, pollination, and water recycling. So there's a lot of other things than just the energy out there that the earth does for us. But we need to remember as we go through this uh, class that some of these, we won't necessarily concentrate on these ecological services all the time. All right. But as we are mining for these and extracting these energies out, we got to remember the disruption to these ecological services. And that's what, as I do as an ecological economist, I put those disruptions in there as well. All right. We will not go too depth into this stuff for our class. I just want you to remember that there's other things. There's the butterfly effect. When a butterfly flaps its wings, it affects other things. Okay, and there's a lot of other things that Mother Nature does for us and just provide us these natural energies. Okay, population growth has amplified our impact on the environment and our energy consumption. All right. And sustainable development is meeting the needs of the present without compromising the needs of the future. Right now, the present, we have about 1.6 billion people here on this earth. And it's estimated that in another 50, 60 years or 100 years, we're going to start getting up to 110 billion, or sorry, 10 billion to 12 billion people here on this planet. All right. So that means if we're going to try to provide for the needs of the present without compromising the needs of the future, we've got to make sure that those 10 billion people are going to have enough energy to be able to function in life. All right. And this is a major new phenomenon in the world. You can see here is the graph of population growth. All right. And it just takes off. And this is what's called your typical J curve. All right. And I love my J curves. It's exponential growth. All right. And not to say that J curves are bad. You just need to stop and watch what's going on because there's something that's happening here. right? And this dramatic exponential growth in the human population was basically driven by our use of fossil fuels during the industrial revolution. Because our extraction, our finding of oil and coal and natural gas, and be able to utilize those, allowed to put our cities and and factories on steroids. The industrial agriculture boom happened. We were able to grow more food with less labor. We had better medicine, better sanitation. I mean, the world just took off. So, this energy use really is a blessing. There's a lot of good things that happened from our use of energy and our ability to be able to extract energy from this planet and use it so it can help us out, right? So it really is a blessing to be able to be where we are today. But we got to remember that, is this really sustainable? Can the earth provide for all this? And the sustainable development programs have come a long way. And what they've actually done is made it into what's called the ecological footprint, right? And we take apart a little bit about everything we use here in the world as an individual, and we put it in this footprint. And we say, okay, we need this much. We use this much for our carbon, this much for our fishing grounds, forests, build up land, transportation, cropland, all these different things. All right. And if you guys want to, you can, when you download this, I won't show this video now, but when you download this presentation, watch Mathis on YouTube about the ecological footprint and understanding how they actually calculate it. But it's basically how much energy do you use as a person, and do we have enough energy here on this earth to be able to provide for that? All right. How much food do you eat as a person? Do we have enough room on this earth for you to be able to grow that food? Right. How much forest do you need? How much carbon? All this other different stuff. Okay. And when we put that into this equation, we see that the Earth can only, it's a limited sphere, right? We only have one Earth, all right? And then we look at how much we actually are extracting. We see that we're on what's called overshoot. So this line right here is what's called the carrying capacity of the Earth. We only have one Earth. And then we count the regenerative rate of all the trees and the fish to be able to reproduce, and agriculture, and all the energy sources that we're sucking out. We know we have there, how much we have left, all this other stuff. And it shows that we are in what's called overshoot. All right. So humans, renewable resources right now, right, our energy that we get from the sun shining every day, 68%, we're using it 68% faster than they are being replenished. All right. So we are in, I think, fast motion doing the story of the Lorax. We're cutting down the trees 68% faster than they can regrow right now. We're sucking out the oil out of the ground 68% faster than we can find it, or that it can regrow too. Okay? And this is called overshoot. And this is something I'm very concerned of as an ecological economist and, a dad and everything else. Because we can't continue living the way we're living without the future generations being extremely hurt. And some of this has to do a lot of this has to do with our energy consumption and what energies we use and how much we use it. But there is hope we can actually get by this and try to reformulate things, because now we're able to, with this ecological footprint, we're actually able to equate what we're using. All right. So when we do this, we see there's a pretty big disparity. We see that about 20 of the wealthiest nations have about 55 times the per capita income of the poorest. And this extra money allows them to use more land. So what this footprint says right here, it says the United States is using about 8.6 hectares for the average citizen to survive. That's 8 hectares more than the average Haitian. All right, 3.5 more than the average French person. All right, India has 1 billion people. We have 330 million people, and they only use 1.1 hectare per person. All right, China is using 3.6, and they got 1 billion more people than us too. All right, so there's definitely a disparity amongst our consumption of energy and resources between these nations, and it's usually due to the wealthier nations consuming more. All right, and then we need to decide as a society. We use a lot of energy here in the United States. Okay, are we going to cut back on some of ours so we can have the Haitians have a little bit more to make it more equal, or not? That's something we need to decide. And you can make up your own mind. I'm not here to tell you what to think. You can make up your own mind. And as you go out into the world and start implementing some of this stuff in your own lives, you can, decide what you want to do. Um, so the energy choices we will shape our future no matter what. Okay, we definitely have to decide what we're going to do in the future because there's not only this environmental justice we just talked about before. There's some limits that we have definitely breached in this world, and we're going to have to start to address them. So we're going to talk about those as we get through this class. So our reliance on fossil fuels is one of the best examples of how our resource consumption amplifies environmental impacts. All right, we definitely can see that. Even Exxon knew that when we started burning this oil way back when in the 1980s, that it was going to cause global warming. They definitely knew. So did Chevron. There's two papers out there that they were the same as everybody else back in the 1980s. Fossil fuels have allowed us to power the machinery, industrial revolution, increase our crop yields, and run vehicles and transport networks. I mean, it's done some great things. We definitely have had, we've had a great run at it, folks, right? But fossil fuels are non-renewable. They generate a lot of pollution, they disrupt our ecosystems, and they're extracted and transported. So there's a lot of downfalls to them. All right, and what I do as an ecological economist is I actually look at things and I put in what's called negative externalities. And those negative externalities are the pollution and disrupted ecological services that we lose by extracting these fossil fuels, and that is a cost to society. And what I'm trying to do is I work with others. We try to put a price tag on that. So when you're pumping your gas, you're actually paying for that pollution, not somebody else down the line. Okay? And that's what we're trying to figure out as a society, whether or not I've ever learned or heard of the term a carbon tax, which we'll talk about later in this class. All right, and that's part of that. All right, pay for your part of global warming. All right, because carbon is definitely what we're going after most of the time in this energy cycle. All right, and carbon is found in all organic molecules, including carbohydrates, fats, proteins. It makes up all living things. So there's, carbon is we are carbon based life forms. Okay, our fossil fuels are carbon based, and what we're actually doing is disrupting this carbon cycle. All right, because we're taking all this ancient. Let's just go to this next slide. Okay, so what we're doing is there's a natural cycle in before the industrial revolution, the parts per million in the atmosphere, carbon in the atmosphere, CO2 in the atmosphere was about 280, 350, it fluctuated during that time of our becoming humans. All right. And that's been kind of constant for, thousands and thousands and thousands of years. Okay. But since the Industrial Revolution, we can see that there's been a spike in the carbon dioxide emissions. Okay, and we know that that's brought to us by us because this cycle can be tracked. This little circle here, and we're taking these fossil fuels out of the ground and adding more little tiny balloons, little molecules, CO2 molecules, into the atmosphere. And we know, thanks to the laws of physics, that when that sun shines down through the atmosphere, hits down off the earth and then bounces back out, it gets caught in these little balloons, these little molecules, the CO2 molecules in the atmosphere, and adds latent heat into the atmosphere. Now, if we didn't have these CO2 molecules in the atmosphere, we would be freezing. All right, we would be below zero. We would be living on an iceberg. It would be one big ice cube. That's what the Earth would be. So CO2 is definitely important, right? And during a nice stable time with 280 parts per million in the atmosphere, we were just living high in the hog for 1,000 years. And then we started taking out all this stuff, all the CO2, and putting it back up into the atmosphere. And now we're making it warmer. We have about 400, I think the last reading was 411 parts per million down there in Hawaii. So we've gone from, a nice stable 280 to 350, kind of never, those are the two extremes basically, to now 411 parts per million in a matter of 20, 30 years, not 1,000 years like it's taken for those fluctuations to happen. Okay. So that's basically what we're doing. It's all of our energy from this fossil fuels, and we need to decide as a society, what are we going to do? When you listen to the COP, there's what's called the Paris Accord agreement, right? The Paris Treaty, and a lot of people will say, hey, the Paris Treaty didn't, only take down the temperature by 1/10%. Doesn't do anything with the temperature of global warming or anything. That wasn't the purpose of the Paris Accord. The purpose of the Paris Accord, we had all the nations get together and say, hey, we're going to stop putting the CO2 into the atmosphere. That's what it was. It was about CO2 emissions. It had nothing to do with temperature. And what we're trying to do is to get down to that 350 level. All right. First, we're going to need to stop what we're adding. All right. And then once we stop adding more and stop that from going from 411 to 412, then we can start thinking about sequestering it, all right, and trying to get it back in the earth and forming some more fossil fuels. And that's going to take some trees and some algae and some other things, all right? So that's what we're doing with our energy cycle, all right? With the carbon cycle, we're just disrupting it as humans, okay? But there are sustainable solutions that abound for our energy consumption. All right, we can use renewable energies if we properly manage them. All right, soil conservation can help us higher, in our agriculture also for higher efficiency irrigation and start putting some organic agriculture to make our food consumption more sustainable. Believe it or not, because about 80% of your food cost actually comes from energy. Being able to drive those heavy machines for harvesting and getting it to the grocery store and all that other stuff. Okay. Our technology is becoming more efficient too. So we're definitely able to save some money. And that's why I love the engineers out there in the world being able to recalibrate some of these things out there and make them more efficient. Laws and technology that's also reduce our air pollution. America is one of the best places in the world right now. Like shows if we pollute things, we can actually clean them up. I really like how Pittsburgh's done it. My grandpa used to go down to Pittsburgh downtown and have to bring two shirts. Halfway through the day, his shirt used to get all sooty from the coke plants, steel plants down there. All right, and he literally had to change his shirt halfway through the day. All right, that doesn't happen here in Allegheny County anymore, in Pittsburgh anymore. It's not the cleanest. We definitely do not. Our air quality in Allegheny County is still not good. All right, but it's not as bad as it was. So we can clean this stuff up. All right. We've also tried to identify some endangered habitats and some other species, and our ecological services out there to be able to protect them a little bit better. Okay, so we definitely do have a lot of solutions here, and in this class we're going to talk about how we can find solutions to the energy part. Okay, because matter, chemistry, and energy, understanding the environmental science requires knowledge in the basic properties of matter, energy, and chemistry. All right. So matter is defined as any material that has mass or occupies space, and chemistry studies the interaction of this matter. All right. So we're not going to get too heavy into, um, the interaction of some of this chemistry and stuff like that. But you've got to make sure that matter is anything that has occupied space, and chemistry is, the study of how that matter divides, right? Because there's a chemistry to olive oil. We're actually going after different carbon chains. All right, and each carbon chain has a different bang for its buck. Right, and there's different grades of oil you'll learn about, different grades of coal you'll learn about, different grades of natural gas you'll learn about, and each one of these have a different kind of carbon chain, which gives us a different heat value, which gives us better efficiencies. Okay. And matter is always conserved. All right. So the first law of thermodynamics is the law of conservation. which states that matter can't be transformed from one type of substance to another. It can't be created or destroyed. All we're doing is kind of moving the molecules around. All right, matter is in an ecosystem continually cycles. It always goes through. Sooner or later, we will have some more coal that will be formed underneath these layers of Earth, even if we're not here or not. Right? So it's constantly cycled. It just takes a little bit longer to make that coal than it does a tree and just burning of the wood. All right, and undesirable matter like nuclear waste and pollution can't be destroyed. It's always going to be with us unless somehow we can jettison it out into space and say goodbye. All right, but it's still going to be out there in space. It will never disappear. As much as I loved Hillary Clinton, she was a wonderful person, all right, or whatever, or what have you. Okay, I remember one time she was in the debate and said we were talking about the Flint water crisis, and she goes, "I don't want to just fix lead and Flint. I want to get rid of all lead." And I was like, "Oh, you can't get rid of all that. It's got to be here on Earth unless we put it up on a space shuttle and take it to Mars. But then it will still be on Mars." Okay? We can't create or destroy matter. We're talking about those molecules. You look at the elemental charts out there, the chart of elements. All those things, they're broken down to the final parts. And what we have, we have. And we're just moving them around. Okay? And sometimes they become unusable. All right? And that's what we're talking about when we're talking about the second law of thermodynamics. All right? The nature of energy tends to change from one more order to less orderly state as it changes forms. All right? And just think about this with a lump of coal. All right? It's nice and orderly in this little block, and then we set it on fire, and all those molecules, they don't disappear, they just go up into the air, all right, or into the ash, and then become unusable for us. Okay, lickety split. Okay, and that's what the second law of thermodynamics tells us. The first law of thermodynamics tells us we can't create or destroy matter, and second law of thermodynamics tells us every time we use matter, it goes from more order to less disorder, to more disorder. And for example, here you see the logs on a fire, right? So we have a nice little orderly fire out here. We light it on fire for the energy, right? And we got the HO2 and CO2 and like heat waves flowing out, and sooner or later it increases in entropy and becomes just ash, right? And maybe these CO2 molecules, right? It's going to go up in the air and trap some latent heat up there, but someday maybe it will be pulled into a tree and become another tree someday. All right, the carbon will be put into the trunk and the oxygen will go back out and look for somebody else to start another fire so the carbon in here can go out and hook up with another oxygen molecule. Okay, so this is our what's called potential energy. This is what's called our kinetic energy, and then it finally goes into entropy, where we can't use that energy anymore. Right, and these are basically done into the laws of thermodynamics is also a equations for this. All right, mathematical equations. What this just talks about, the change of heat for us into the two different surroundings. All right, and that the cold always the hot's always going to try to infiltrate the cold, and at the very end it becomes zero. Right, we're going to have perfect no order or no disorder. It's going to be the temperature of space out there. Right. So there's different kinds of forms of energy. All right, energy can be either kinetic or it can be potential. All right, and kinetic is just energy in movement, and potential is stored energy, that lump of coal. All right, and energy in movement is that fire, the heat coming off, or the sunlight coming down, or that tree, or that car going forward. Okay, um, energy comes from energy comes from moving, right? So thermal energy, you have to have kinetic energy, you have to have movement, right? So thermal energy is just the moving particles of the heat dissipating from that fire, right? The mechanical energy is the object of motion. So we put that heat going into our gas tank, our gas can, head off those pistons, right? And that turns that mechanical energy, that piston, and our tires to go around in our not our piston. The piston goes off and it turns that crankshaft that makes our tires go round and round and round, right? But we also have electrical energy, right, which is energy from particles moving within inside of a wire, right? So those are those electrons going to, the negative electrons chasing that positive electrons, all right? And we do this also in our cars, right? We take that electrical energy and make it into mechanical energy instead of burning that gasoline and making that piston go up and down that turns that crankshaft. We just take the electricity right to the wires and we turn that crankshaft on our tires. Okay, and we also have what's called magnetic energy. Okay, these are kind of like those power trains that you see. They actually, or a roller coaster you might be on, right? So the magnets will actually cause a push or a pull. All right, take two magnets together, they either stick together or push together or pull apart or push apart, right? And that's what we do on those uh, roller coasters. They were actually done on magnets, so we got the opposite poles slowly pushing or I guess you should say quickly pushing that roller coaster forward. Okay, because the opposite poles are pushing them at the time they have. All right, and we have what's called sound energy and light energy, the energy that we hear, and then the light energy that we see things with our eyes. And we also have our list of potential energies, okay, which are chemical energies which are stored. Okay, so food is a chemical energy. Okay, it's stored in those plants, and then we take it and we release it through our caloric intake. Okay, and our energy, our walking, breathing, and everything else. All right. Batteries are also a chemical energy. Okay, they're stored in there for later, and then we start up our cell phones, and we got that electrons running through. Okay, there's also what's called elastic energy, which is energy which is stored in objects that are stretched real long. So a slingshot or a bungee, or when that bungee cord goes all the way down, that's your elastic energy. It's going to bounce back up. Okay. We also have nuclear energy. We won't really discuss too much of the nuclear energy section here in this class. All right. Um, it's a little bit over the. I'm not. It's very expensive. One. All right. But nuclear energy is actually pretty darn good because that's what's kind of happening in the sun there. All right. So we're just not going to go over nuclear power. Okay. Gravitational energy also, that's energy stored in an object when it's above the Earth's atmosphere, okay? Or not the atmosphere, above the Earth's surface. So our hydroelectric dams are all gravitational, right? So we store that water up top in a big huge lake, and then all of a sudden we run it through, and that water running through that little pipe goes and turns the turbine, which makes those magnets go around those copper wires, and that gives us electrical energy, and then all of a sudden we got Vegas. All right. So the forms of energy: kinetic and potential. All right. Thermal, mechanical, electrical, magnetic are usually makes our energy in motion. All right. Potential energy are our batteries out there, our slingshots, our nuclear energy, and the the stone on top of the hill. All right. But don't forget also that sound and light are also part of our energy mix. Um, when we look at in this class, we're going to look at different types of energies. One of the energies we're going to look at is called biomass, right? And that's the conversion of solar energy into chemical bonds and sugars. It's called our primary production. So when we get our um, energy, all of our energy comes from plants, basically. All right, and that wonderful surface of being able to convert sunlight, the energy of sunlight, into chemical bonds, the sugars and carbohydrates and proteins and nucleic acids that we eat in that food. I mean, it's amazing. And without that, we would have no other energy. So they are the primary producers, all right, of our energy production here on Earth. Even our fossil fuels are just ancient primary producers. Coal, natural gas, and oil all came from biomass ancient years ago that just turned into fine French wine for us. That's all. All right. But they are basically biomass. Okay. The total chemical energy produced by these by plants, all right, autotrophs, it's called the gross primary production. So the energy that remains after respiration is used to generate the biomass leaves. It's called our net primary production. All right, so we have the gross primary production of how much energy they consume to grow, All right, and then the net primary production is basically what's left over for us to use. Okay, energy used by consumers to generate their own biomass is called secondary production. So we're all second half, right? We're, after the plants, all the animals and species they're called the secondary producers of biomass. Okay, so you are a bunch of biomass, but you're secondary. You would not exist without the primary producers of the plants. So the rate in which energy is converted into biomass is termed as productivity. There's a lot of places that are faster. All right, of taking that as sunlight uh, uh, into their biomass and making that chemical production. So the energy or biomass that remains in the ecosystem after the anaerobics have metabolized enough for their own maintenance through cellular respiration is called the net primary activity. So we see what's left over. So the algae beds and reefs, all that algae and stuff like that makes us a lot. There's a lot of biomass in there in that seaweed. Okay, tropical rainforest. Like I said, we talked about that diversity thing just a little bit ago. Because both of these have a lot of diversity in these um, coral reefs and a lot more resilient as an area. All right, but then you start getting into the tundra and the open oceans and the desert. You can see there's hardly any primary productivity or net primary productivity for us humans to actually extrapolate from. That's basically why most of our stuff is actually, cities are actually built in these type of areas because there's a lot of biomass and a lot of energy that we can get out. Okay. Freshwater wetlands and tropical forests and coral reefs and algae beds tend to have the highest net productivity, like I said, and deserts and tundra and open have the lowest. Okay. So humanity has devised many ways to harness these renewable and non-renewable forms of energy available to us. Okay, and here's just a helpful list of things we primarily use. All right, here as a species. So coal, natural gas, oil are all we consider non-renewable resources. Okay, the fossil fuels that come in a solid, a liquid, or gas, right? And we can't really get these back for millions of years. All right, nuclear energy that we're using in our nuclear plants, it's considered non-renewable as well. All right, so once that uranium is actually depleted, it's going. I kind of think of these a little bit different than some of the nuclear energy a little bit different because it can last for 50 years. Once we burn that chunk of coal, it's gone. But once we get that uranium and get it up to that little steady state, and then eventually it will start losing its energy capacity and become unusable. But it's a little bit different. Not just me. I think it shouldn't be in a non-renewable. I think it's just uranium is a piece of matter, just like hydrogen. All right. But we also say that hydrogen, it's not even on here, is renewable energy. All right. Biomass energy, hydropower, solar energy, wind, geothermal, and ocean energy all are what's called renewable energies. Right. They usually come back with inside of a lifetime. All right. Biomass usually a plant will grow so we can use it with inside of a lifetime of an individual. Trees take 80 years, hunt takes 6 months. Okay. Hydropower would be our power from the water from our dams. Okay, solar energy, wind, geothermal. We'll have separate sections on this class about these sections. We won't really talk about ocean energy, but I just get the energy from the tides and the waves. All right, and that's actually from tides and waves are what a form of gravitational energy, right? Of the moon pulling on the waters, right? Uh, Society relies mostly on these what's called fossil fuels or non-renewable energies. Okay, over 80% of the energy used worldwide come from three main fossil fuels: oil, coal, and natural gas. All right, and you can see here is the non-renewables that we actually have, all right, that we use. And I hardly say, like I say, when you add in the nuclear and hydro, that's a big part of this. So, only about 11% is actually what I would consider the solar or the wind and the biomass that we're, or biofuels that we're actually going to cover, all right? Because we're not even going to put in this hydro and nuclear parts, all right? Because they're kind of basically saying, um, here we're just making electricity. We're just boiling water to make some steam to turn a turbine, all right? Coal, natural gas, hydropower, all this stuff over here is the world electrical generation. So energy production by source, all right, and how we get our electricity is mostly done by coal, all right, and natural gas is getting a little bit bigger, all right. Our dams are about 16% of all of our electricity comes from dams, and one reason why I don't really cover this as much as I should, but I always say when we're really here in the United States, especially, we're not going to really get any more dams. We've already dammed up every damn place we can dam. All right, we've really have utilized that gravitational force of energy as really, really efficiently. We'll probably go over a little bit about the small little dams we're building to help out some of the small little communities around the world that live on a stream or something. It really doesn't. It's really neat. All right, but it's smaller. All right, you could build it for like an off the grid kind of source or a cabin in the woods or something like that. All right, and then nuclear is 10%, right? But it's still our renewable energies, bioenergies, and renewables is only 6.3 of the world's electrical consumption. So we need to actually flip this around. In my humble opinion, we need to have bioenergies and renewable energies take up this part, right? And then fossil fuels take up this green little part. Right? You notice also here that oil is only about 4.3% of our electrical consumption or electrical production. Right? We save oil for our transportation, and we'll find out that a little bit later. Okay. Now, energy is also unevenly distributed throughout the world. Right? I already mentioned Adam Smith, Wealth of Nations, and one of a nation that has the energy is going to be the wealthiest, and it is going to be pretty wealthy. But that doesn't necessarily tend to be totally true. All right, going to see here Venezuela has 17% of the world's oil reserves, and that country ain't too wealthy. All right, Saudi Arabia though they have 15. Man, they live with high hog in Saudi Arabia. Canada has 10, Iran, and then Iraq. All right, so just because you have one of the most precious natural resources known to man, doesn't mean that you're going to be automatically hitting the rich. Okay. Natural gas, you see Iran, Russia, Qatar, Turkmenistan, and the United States has finally made one of these lists, but we only have 4.7% of all the natural world reserves. All right. So we're not really, dominant. I've heard some people say that Pennsylvania is going to be the next Saudi Arabia of natural gas. I'm like, how's that going to be? I mean, how's Pennsylvania going to be in the next Saudi Arabia? We have 4.7% of natural gas. They have 15% of the oil. All right, we're not even going to come close. All right, but the United States, we do have the most coal. All right, 22.1% of the world's coal out there. China is second. Russia is third. And Australia and India are rounding out the bottom two. Okay, so it's not evenly distributed throughout the world. All right. There is the estimated U.S. energy consumption in 100 quad. So this graph is one of my favorite graphs. So it shows the breakdown of how we actually use our energy, how we use our solar, our nuclear, hydro, wind. Okay, so this is the energy source, and this is what happens at the very end. So most of our solar, right, goes into residential, commercial, and industrial. None goes very little. You see a little bit of our renewable energies. Okay, going from the electrical into our transportation. And that's what I was saying before. Our oil, very little is ever used for electrical generation. All right, up in here. Okay, the rest is actually used in transportation. So all our transportation is basically subjugated to petroleum, to the fossil fuel of oil. And we are in a predicament, which we'll talk about during the oil section. We need to kind of convert over to a biomass or maybe a hydrogen or something else, right? Because we're going to learn we don't have too much oil left, okay? And then you see here at the end, they have the rejected energies, 67.5 quads of energy is actually rejected energy, wasted energy out of the system, all right, due to inefficiencies of our electrical generation or our machinery. All right, so we are very rarely, really inefficient of capturing this energy throughout the whole system. All right, but we do get some energy services back through the ecosystem. These are some of those ecological services I was talking about, the biomass, the primary productivity, and things like that. We do get some quads back, 32.7 quads put back in the system just through these natural systems. Okay, and it's a pretty famous chart. All right, and you can see if you read the footnotes, of course, it comes from the EIA, the Department of Energy. All right, so all these stats is just a compilation of different things you can find on the EIA website that you're gonna go through on that homework assignment. Okay, so it takes energy to make energy. So harvesting energy requires the use of heavy machinery, construction of roads, pipelines, waste ponds, and it takes money. It takes money to make money. It takes energy to make energy, and every time we use energy, we have a little bit less to use. So we'll never get. There's no such thing as a perpetual machine. There's no such thing as something that's going to give us more energy at the end. All right, those are the laws of physics. Okay, every time we use energy, we've got a little bit less, and it's going to start dissipating. We're not going to be able to capture everything. Although this number right here, we can definitely do better. All right, this rejected energy, we definitely do better of capturing some of this stuff. All right, but we still ain't going to be 100% of not getting, not having any rejected energy. Okay, it's going to happen. Okay, and net energy expresses the difference between energy returned and energy investment. So when we look at our cost benefit analysis and do all this other mathematical looking what's the best energy source, we look at net energy. So energy returned minus the energy invested. How much energy do we get back compared to how much energy we put in there? And that's one of the biggest problems that's happening today, is that we are actually spending, put it simply, the low hanging apples have all really been picked when it comes to fossil fuels. Okay, so we've been able to just reach out there. I mean, Jed, I don't know if you guys ever heard of the show called Beverly Hillbillies. All right, this guy goes out and running and shooting at a squirrel and shot into the ground, and up come a bubbling crude oil, that is black gold, Texas tea, and the guy becomes a millionaire and moves to Beverly Hills. All right. Those days of shooting at the ground and having bubbling crude coming out are over. All right, but it was true. We actually were doing that. I mean, someday research Oil City here in Pennsylvania. All right, that's where the first oil well was ever erected. All right. Unfortunately, there is no more oil. The Oil City's still around, but there's no more oil coming out of there. Pennzoil, Pennsylvania oil. All right. So energy return minus energy invested, and now it's getting a lot more expensive. So now we actually have to get that ladder out and put on a harness to try to go get those apples up there in the tall part of the tree, right? So it's getting a lot more expensive, okay? The energy sources are assessed by using the EROI, energy return on investment, which is calculated by energy return divided by energy invested. All right, and what we want to do is we want to have a lot of energy, stored energy coming out of those oil wells or coal firing or coal plants, coal mines or whatever. All right. So the EROI ratios for conventional oil and natural gas in the United States have declined from 24 to 1. So every barrel of oil we put in before, we were getting 24 barrels out. Every gunshot, every gunshot that Jed put in the ground, he would get 24 barrels out of the ground from that gunshot. Okay. Today, though, every time that Jed puts something in the ground, shoots in the ground, he's only getting 11 barrels of oil. Okay. So definitely the energy return from our discoveries have definitely declined over time. And we're starting to get these ratios smaller and smaller. But sometimes that's a good thing. That means sometimes the solar and the wind and the renewable energies can actually now start competing with the fossil fuel energy. So it's more economical to switch over because it's a lot more expensive to blow up that mountain than it is to put some wind turbines on top of it and collecting the energy that way. Okay. So where will we turn for energy? Enormous amounts of energy, money, and technology are now being used to extend our reach for fossil fuels. So oil, gas wells, we'll learn about some of the techniques they use in this thing, and again, drilling deeper and the places where that once were unreachable, but now are reachable. Okay, and we need to decide if we're going to use these new resources such as oil sands and shale to run our economy on, or if we're just going to go straight over to biofuels. We're going to need to make that decision here. Okay. But when it all comes down to it, economics is really going to determine how much will be extracted. So the proportion of fuels that are physically accessible to us are called technologically recoverable, right? And when you see those, when you do your EIA assignment, the proven reserves are actually technically recoverable reserves. Okay, in that little worksheet, in that first little diagram. All right, so I asked you where, how much do we have in there? And we know the United States thinks it has in the grounds. Those are the ones that they think they can actually get out. So, and we still have some that we know that aren't. It's not really technically recoverable. Some of the methane hydrates in the bottom of the ocean just aren't technically recoverable at this time. Okay, maybe someday they will be. Okay, but right now they are not. So the economically recoverable portion of the fuels depends on the cost extraction and the market price, of course. No one's going to go into business when it doesn't make any money. And the proven recoverable reserves are both technically and economically recoverable, right? So the proven ones that you see on the thing have the technologically recoverable, and it makes sense. I don't know about if it's economically recoverable. So I don't think that some of those on that website that you see, like oil, fracking right now at the price of gas, at oil being $35 a barrel, maybe even 40. It's between 40 and 35. It's been ranging in the last couple of weeks. That price per barrel of oil is not going to allow the frackers, which we'll learn about, the oil frackers, make money. They need about $70 a barrel to break even. Right, so those aren't even economically recoverable. So that's but technically yes. All right, economically no. Okay, but we'll talk about that a little bit more in the oil section. All right, so economics determines our extraction. So this table shows the amounts produced and consumed by the leading nations. Of China is the world producer of coal and the world consumer of coal. All right, the United States produces the second producer and only the third consumer of that coal. Okay. Also, you look here at the oil production. United States, we had 4.7 on that one graph. Amount of oil in the world. All right, so we had 4.7% of the world's oil, but we are really the number one producer. It's amazing, folks. This happened in 2018. I think we became the world's number one producer. All right, and that's all that fracking that I just talked about, all that shale oil that we're getting out of the ground, right? Because oil, believe it or not, it might be only about between 35 and 40 bucks a barrel right now. It used to be 100, all right? 5 years ago, it used to be $100 a barrel, and fracking went crazy. Now you're making 30 bucks a barrel, Before you're making 70, not even breaking even at 70. Now you're making 30 bucks a barrel. It went crazy, hog wild, right? So don't expect this number to last too much longer for number one production. All right, but expect our consumption level to be there. All right, we use 20% of all of the oil out there. All right, we consume about 20 million barrels of oil a day here in the United States. 20 million barrels a day. We have 5% of the world's population and consume 25% of the world's natural resources. It's amazing. All right, so yeah, I don't know how in the heck we are number one in production, but we are. Good thing. Jobs, 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 baby. I guess. Okay. And we're also number one in consumption. Okay. Saudi Arabia is the next in production. All right. And then Russia and Iran and Iraq. All right. And these are all part of what's called OPEC. And we'll talk about that during the energy section. But the next consumers, China and India are the next biggest, and they each have 1 billion more people. So these are 2 billion people. India has 1 billion more, and they're only 4% of almost 5% of the world's oil consumption. The United States, 330 million. Okay, they have 1 billion more people. Unbelievable. Now, in natural gas, United States, once again, it went to production. Okay, I can't remember how much we have in production. Maybe that was natural gas that were 4.7% natural gas. Yeah, oil, we have less than 4% of the world's oil, I think. Okay, United States is number one also in the natural gas. Okay, so it's a big money. All right, talk about an engineering job. You can figure out how to get that liquefied natural gas out there on a ship and out to Europe, where it's $10 a cubic foot instead of $3 a cubic foot here in the United States. You're a millionaire. All right, you got it going on. All right, people are trying. There's engineering jobs cracking down the walls trying to do that kind of stuff. All right, so you can see we're number one in production and also number one in consumption. But we also have probably the least amount of, we're like fifth in natural gas. All right, Russia, Iran, Qatar, and Canada are number one, or 1 and 5, 2, 3, 4, and 5, and then for consumption, you can see it's about the same here. United States is number one. India, of course, has fallen off the list. They don't do too much natural gas yet, but China is in there. Soviet Union, Russia, okay, but they're also the number one, second producer. All right, but this is something they have a lot of on in Russia. All right, they definitely have the highest production rate. So Russia has 12 point. That's the world. This is what oil, coal, natural gas. Oh, that's all I've just gone through. All right. Let me see. Where was that? That was just cool. Here it is. Natural gas. So Soviet Union, Russia is second for natural gas reserves. All right. The United States fourth. So we're not even on oil, or we don't have. We have less than 2% of the world's oil, I think. All right. So no matter what, though, oil and natural energy really makes this world go around. Everybody thinks about oil and natural gas and renewable energies and all that stuff as in just us being in motion and doing things. But like I said, we just move those molecules around, and almost everything we own and use has natural gas or petroleum in it. All right, from your toothbrush to your chair to your TV screen to your window glass. All right, everything takes energy to make. All right, so energy is definitely one of those needs that we have to have as a human. All right, to be able to live. Whether that energy is enough food, or whether or not that's enough electricity to be able to read your readings for this book or for this class during the summertime. All right, I like that. I think that's definitely a need to be able to see during the nighttime. All right, maybe you think differently, but I like to have that need, and that's what we're trying to do in this class: is how to make sure that we have enough energy to go around and everybody can meet their own needs. Okay, and you're going to be asked to make up your own decision by the time this is over. Basically, okay, where do you want to go as a person, and go do what you want to do. All right, but you're going to have the basic foundations at least. All right. So in conclusion, I hope that this presentation showed you the energy is needed for the world, exist. And one of the ideals for sustainable development is for all to be able to meet their energy needs while making sure the future generations can meet their energy needs. All right. To do this, we usually use what's called the ecological footprint to make sure that we're not in overshoot. Unfortunately, as we saw, the world is definitely in overshoot. We're using too much more energy than the world can actually replace on a daily basis, and we are in trouble. So, in my humble opinion, okay, so we're gonna have to start rethinking some things. Okay, although energy and matter cannot be created or destroyed, it will eventually become unusable. Okay, so I should have, although energy and matter cannot be created or destroyed, it will eventually become unusable. We can use it and it'll, fall into that ash of the fire. And we can't really use that ash. Maybe throw it someday into the garden, and then hopefully the tree will grow and we'll have some wood later on. Okay, uptake that ash and all those nutrients in there. The consumption of energy has definitely been rising over time. Right, the cost of extraction of energy is also rising. Right, so we have more people on this earth. Okay, and it's costing more and more to try to get the energy to meet to meet the needs of the present. Okay, humanity's rates of consumption are unsustainable. Okay, we can't carry on the way we're doing. That's just a fact. I'm tired of even arguing. The numbers are the numbers. Okay, but there are solutions. We're going to talk about a lot of these solutions as we go through one section at a time. How we're going to fix the coal industry, and we'll never get rid of anything. We'll never get rid of coal. We'll never get rid of oil. We'll never get rid of solar panels or wind turbines. It's just what is the best mix? What is the best diversified mix that we can put together so if something disastrous happens, like climate change, we can still survive? Okay. So I hope this you enjoyed this little presentation, and I will post it up soon, and it will be underneath this class videos little area where you can find that. So I hope everybody watched the class video for an overview, know where you find your first reading assignment, and know how to do the EIA assignment. And now here's your first lecture. Okay. Feel free to download the PowerPoints too when we have the test, and you can look through them and use it as an open book and things like that. So if you guys have any questions or problems or concerns, please don't hesitate to give me an email or give me a call. Okay? Thanks. Bye-bye.